It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we're going to talk about the magnetic force acting on a current carrying wire, which is very similar to the magnetic force acting on a moving charged particle. So if we have a current carrying wire, we have a positive terminal and a negative terminal. And the standard convention in physics is to follow the direction of positive charges going from the positive terminal to the negative terminal. So we're going to apply the first right-hand rule just like we did in the previous video. And for that, we're going to look at a few examples of me and my assistant.
Welcome back, everybody. We're going to continue doing practice problems with the first right-hand rule, except this time we'll be looking at a wire instead of just a single charge. So in the first example, we have a north magnetic pole on the bottom, south magnetic pole on the top, and the wire is in between the two. Just like the previous problems, we want to look at the direction of the positive charge. And the positive charge inside the wire goes from the positive terminal to the negative terminal. So we're going to point our thumb to the right from the positive to the negative. Our fingers still go from the north pole to the south magnetic pole. So they're going to face upwards. And our palm represents the direction of the force acting on the charge, or in this case, the wire. And it's going to push the wire into the wall. So the force is directed into the wall. If we wanted to symbolize that, we could draw an X on top of the wire and label it force, signifying that the force is going into the wall. Okay, let's do another practice problem, please. Thank you. In this case, we have the north pole on the top, the south pole on the bottom, and the wire is going out of the wall. We're going to assume this is the direction of the positive charge, so it's going towards the negative terminal out of the wall. Our thumb is going to represent the direction of the positive charge inside a wire. It's going to go out of the wall. Our fingers represent the direction of the magnetic field lines going from the north to the south magnetic pole. And we can see that our palm is facing towards the right. Therefore, the wire will be pushed towards the right, so the force acting on the wire is directed towards the right. And I think that's it for today, but if you could scroll down just to double check. Sweet. Well, if you found this video useful, please like and subscribe on YouTube. See ya.
I hope you found that video useful. So let's come up with a formula to calculate the force acting on a current carrying wire. From before, we calculated the magnetic force acting on a moving charged particle. That was F equals QVB sine of theta. If we remember from before, velocity is the velocity of the charged particle. If we assume it's moving at a constant velocity, we can calculate it by doing distance over time. So F equals Q, distance is the length of the wire, divided by the time, times the magnetic field strength, times the sine of theta. We could see in here that Q over T, the charge per time, is equal to current. So we could change this formula to F equals I LB sine of theta. So why don't we do a few practice problems together? Practice problem number 1 says, a proton moves with a speed of 1.00 times 10 to the 5th meters per second through Earth's magnetic field, which has a value of 55.0 microteslas at a particular location. When the proton moves eastward, the magnetic force acting on it is directed out of the page, and when it moves northward, no magnetic force acts on it. Letter A says, what is the direction of the magnetic field? So why don't we write down our knowns first? We're told we have a proton, so its charge is 1.60 times 10 to the negative 19th coulombs. We also know the mass of the proton to be 1.67 times 10 to the negative 27 kilograms. The velocity of the proton is 1.00 times 10 to the 5th meters per second. And the magnetic field strength is 55.0 times 10 to the negative 6 teslas. So why don't we draw a picture of what's going on? We're told the proton moves eastward. So we have a positive charge moving to the right. And we know from the problem that when the proton is moving eastward, the magnetic force acting on it is directed out of the page. So we could represent a dot to represent the magnetic force acting out of the page. Using the third right-hand rule, our thumb is pointing towards the right, and since the force is pushing it out of the page, our palm is going out of the page. And as we could see, when we do this, our fingers are pointing upwards, which means the direction of the magnetic field is going upwards. So that's the direction of the north magnetic field lines. So we could say that the magnetic field, or the B field, is going upwards. And this answer makes sense because we're also told that when the proton is moving northward, it experiences no magnetic field. And that's true based on the fact that it's parallel to the magnetic field when it's moving north. So letter A, what is the direction of the magnetic field? The direction of the magnetic field is north, or we could say towards the top of the page. Okay, letter B. What is the strength of the magnetic force when the proton moves eastward? So we know the charge, the velocity, and the magnetic field strength. So we could use F is equal to QVB sine of theta. When the particle is moving eastward, it's perpendicular to the magnetic field, so the angle they make is 90 degrees. So the force is 1.60 times 10 to the negative 19th coulombs times 1.00 times 10 to the 5th coulombs times B, 55.0 times 10 to the negative 6 teslas times a sine of 90 degrees, which is 1. When we plug and chug, we get a force to be 8.80 times 10 to the negative 19th newtons. Okay, and letter C asks us, calculate the gravitational force on the proton. So letter C, we want to calculate F sub g. We know the mass of the proton, we know the acceleration due to gravity, so F sub g is m times g. Plug and chug, 1.67 times 10 to the negative 27 kilograms times 9.81 meters per second squared. 9.81 meters per second squared. We get F of g to be 1.64 times 10 to the negative 26 newtons. Notice that the magnetic field, the force of the magnetic field is much stronger than the force of gravity. Okay, let's do another problem, this time with a wire. So this is practice problem number 2. A wire carries a current of 22.0 amps west to east. Assume the magnetic field of Earth at this location is horizontal and directed from north to south, and it has a magnitude of 0.50 times 10 to the negative 4th Teslas. Find the magnitude and direction of the magnetic force on a 36 meter length of wire. So we're also told the length of the wire is 36.0 meters. Okay, so let's look at the direction first. We're told that the current goes from west to east. So if we draw our wire, we know it goes from the positive to the negative terminal, so it's going from west to east. We're also told that the magnetic field is from north to south, so we could draw two magnets, north on the top, south on the bottom, and they're showing us the magnetic field lines are going from the north to the south pole. If we use the third right-hand rule for this, our fingers are pointing in our thumb is pointing in the direction of the current in the wire, so it's going towards the right. So our thumb points towards the right. Our fingers point from the north pole to the south pole, so we have to have our fingers pointing down while keeping our thumb pointed to the right. Sorry, I know it's hard to see on my screen. And as you can see, our palm is facing into the wall or into the page. So the direction of the charged particle, we could say, is into the page. So that's the direction the wire will get deflected. Okay, we also want to calculate the magnitude of the force. We know the current, the magnetic field strength, and the length. So we could use F is equal to ILB sine of theta. They're at a right angle to each other, so our angle is 90 degrees. So we have F is equal to 22.0 amps times the length of the 36 meter wire. The magnetic field, 0.500 times 10 to the negative 4 Teslas times the sine of 90 degrees. Plug and chug, and we get a force to be 0.0396 newtons. And again, it's going into the page. Hope you found this video useful. Please like and subscribe, and I'll see you next time. See ya.